All right, so today we're going to talk about leveraging Go and some of the components within Go to build a functions as a service platform. The core, well, quick about me, get rid of this slide real quick. Software engineer, I run Golang Phoenix. We meet monthly. I also co-organize the BSD Phoenix meetup. Not as much interest in that group, so we don't meet as often, but maybe this talk may spark a little bit more interest. And these are my two Great Dane puppies who are about 110 pounds bigger than that at this point. So, function as a service. Everybody's doing it. All the cloud providers are offering services. And there's even install yourself platforms like OpenFaaS, which is fantastic. It sits on top of Kubernetes, uses Docker, and also arguably, let's see, HashiCorp Nomad could be considered a FaaS platform depending on its use and configuration. So why would I want to build one? Well, Docker's fine, but Linux isn't ubiquitous. The GPL sometimes makes that difficult just due to the nature of the GPL. Sometimes there's the need for using an operating system that is actually free in terms of freedom. So FreeBSD fits that bill. The BSD license actually provides you freedom where the GPL doesn't, but this isn't a religious talk on licensing. So let's move past that pretty quickly. What do we need to build our platform? We need a few core components. We need FreeBSD, we need ZFS, and we need Go. Go is going to facilitate all the software that pins everything together. If we want to think about this in Docker terms, which is probably more familiar to most people, our images or our containers themselves are going to be ZFS snapshots, and jails are going to be the actual execution context from the operating system that segment execution for our applications. So, quick intro to FreeBSD Jails. Show of hands, who's familiar with FreeBSD or even FreeBSD Jails for that matter? That is remarkable. That is a fantastic show of hands I honestly did not expect. Okay, so just quick intro. FreeBSD is a open source operating system under BSD licensing. It's a direct descendant of BSD Unix. If you go through the commit history, you can actually find 40-year-old commits in there. So there's 40 years of understanding mistakes and fixing them. Also serves the majority of the traffic on the internet. Most people think, like I said, Linux is ubiquitous. However, Netflix uses FreeBSD for all of their edge CDN servers, and Netflix traffic being the predominant source of traffic at this point on the internet, at least for the United States, FreeBSD is serving that. Another reason why I chose FreeBSD over Linux was simply the network stack is arguably faster. Also native support for ZFS and dtrace. Anybody familiar here with ZFS or at least dtrace? Okay, cool. So if you know dtrace, you understand how debugging actually works when something goes wrong. So what is a jail? You can think of a jail in Docker terms as a means of segregating a process from the host system. In FreeBSD, though, jails come as its own full service package, so to speak. There's no pinning up of network namespaces, C groups, or process namespaces. You basically call jail2 or the jail sys call with some parameters, and the kernel then takes that execution and locks it to wherever file system you want it to execute to. That's one of the parameters, and then prevents that process from ever escaping that jail. Jails also have their own users and groups, and you can think about jails as operating system virtualization, not necessarily hardware virtualization like a virtual machine where you have an operating install, but or an operating system installed, but the file system as an operating system virtualized. FreeBSD also provides the ability for like a two-way mirror. You can run top and a few other utilities and actually get in and see what the jails are doing and run the system utilities to see what jails are doing, but jails can never escape, or you can't see anything outside of the jails. They're simple to use. They provide the necessary abstractions to provide a secure environment for short-lived processes, which is what we're going to focus in on today through the use of ephemeral jails, as well as long-running processes. Some of the common use cases that you'll find jails in, jails are virtualizing LAMP stacks or providing shell environments from hosting providers. and even application services you can deploy in jails. Let's see. OK, ZFS. And sorry for kind of rushing. This talk originally was an hour, so I had to cut it in half. So ZFS. ZFS was originally developed by Sun a couple decades ago and is a fantastic and unbelievably stable file system. Some of the core features is that it provides snapshots, near instant cloning, and it's extremely fast. Snapshots are basically just, as they sound, snapshots of the file system itself, of the data sets. And they're read-only copies of the data set, so they can't be written to. The creation of them is near instant, and they take up no disk space unless the original snapshot differs from any changes on the file system. So we're going to utilize snapshots in our system to provide for the file system aspect of our jail, so we can segment out the execution space at a file system level, much like Docker images. Another aspect of ZFS that we're going to take advantage of are clones. They're read-write volumes, and clones are a read-write byproduct of snapshots. They're nearly instant to create, and they take up no disk space unless there's differences from the original snapshot themselves that the clone has come from in terms of the data sets. The next component is Go. Why Go? Well, it's the main language I know, so isn't that all of our excuses for the languages we use? Even they may not fit in the right context, but we use them anyway. Go is good fit for this. However, I've rewritten all of this in C, which I may open source. We'll get into that later. All of what I'm going to show you is a full working system. That caveat should not be used anywhere even close to a production environment. However, it's there to maybe take from. So Go, it's extremely fast. There's about 25 usable keywords. There's about 29 keywords in the language, 25. People generally use, the other 4 or 5 people don't. It compiles extremely fast. And you can build complex systems fairly easily, and it has a fairly extensive standard library. You don't necessarily need to bring in a lot of third-party utilities. Because if anybody, raise a hand, show of hands for people's experience with Go in the room. And then raise your hands if you like the dependency management currently. Exactly. So the standard library is fairly usable, but not fairly, it's very usable. So the Go components that we're going to use is going to be NetHTTP. That's going to provide for our HTTP REST endpoint, which is going to facilitate function execution, but also control of the jails, administration, et cetera. We're going to use text template and the Go compiler directly. So let's do a demo. Let's see what this actually looks like in practice. We are going to, so the whole purpose of this is to provide functions as a service to be a literal thing. We write functions as a service currently, but we build very contextually locked applications that do one thing. It's not really function as a service, but then again, that's arguable, and I don't really care to argue about that. This, we have a Git repo under github.com/BrianDowns/smile. And we're going to call the smile function, the literal smile function inside that repo. And when we post that into our system, please work. It worked. All right. We get a timestamp back of when we sent it and a data field. It's kind of not great to see that, but you can kind of see the colon and the right paren giving a smiley face. So let's take a look at exactly. So if anybody has any functions they want to try, you can do that. If you DOS it, it's fine too. I just reboot it, doesn't matter. Also, if you want, try and hack it. All of this is running inside a jail anyway. It'd be kind of fun to see what the results of that would be. So what we did here was we called curl and we posted in a URL, or we post to the URL running the function. And our data payload takes 2 fields. One is a URL, and it's a URL to a Git repository that points, well, to the Git repository. And then we have a field called call. This call is the actual function itself. And any parameters that you would provide to the function, you just put in the call. So whether it's integers or strings or whatever, you just put it in there. You just got to make sure you escape the JSON correctly, so obviously it doesn't break. But you would end up with this. These slides were just in case the demo gods didn't smile upon me. Thankfully they did. All right, so what all just happened? Let's kind of put these pieces together. We made our original call, being the caller, being curl. We take that request and we hit the API. The API then checks to see if we've cloned that repo before. If we haven't, then we git clone that repo from GitHub or any available Git repository the system has access to. We also then go and that gets cloned down to what I've deemed a build jail. In the build jail, we have GOPATH set up, which isn't necessarily necessary anymore after Go 1.11's been released, but this was written before that, so that is the case. We clone into a build jail. We actually build our binary from the function itself, and then we put that binary as being the artifact, and we put that into our execution jail. All of the execution jail and the binary are created upon each call, provided that the Git repo doesn't exist. If the Git repo does exist, we just recompile, or actually, I'm sorry, what we do is we check the cache and we see, do we already have this binary? If we have the binary, we take the binary out of the cache it's stored in, create a new execution jail, put it in there, and actually execute it, and then kill the execution jail. The only thing that remains is the build jail. However, the build jail is only used when actually building the binary. So we can escape having to git clone down each time. So the execution we just ran was a clean setup, and it ran fairly quickly. So it just went out via HTTPS, HTTPS, cloned the repo depth 1 because anything beyond that would be unnecessary and also slower given whatever the size of the repository may be. Compiled the binary, put it into the jail, executed it, and then left. So now that we run it, we can run it again, and then depending on the size or the throughput of our network, it'll be pretty fast because now the binary already exists. It's been compiled. It's just pulling from cache. So next, let's build it. Let's build this system. Let's get into actually how it works. We're going to need a few components to the system. IP management, our execution facility, HTTP JSON REST API. We're going to need a cache layer and client code. We'll get into why we need client code in a few moments. But IP management, anybody who knows or is used to administering, which apparently by the remarkable show of hands, a number of people have dealt with jails. You need to statically assign IP addresses to jails. Generally, there's a system called VNet, which allows for dynamic network allocations. But at the time, I wasn't familiar with VNet, so I had to write an IP allocator. We can't use DHCP because DHCP requires raw sockets, and you can't use raw sockets in a jail because that would require root privileges, and now you've just exposed your jail to having root privileges at the host system level, and that defeats the purpose of segmented execution for at least security concerns. We could use DHCP, it works. However, the pro is that it just works. We don't care, whatever. However, you can't use raw sockets, and it provides a lot more functionality than we necessarily care about. We just care about getting an IP address in case our function code needs to communicate. So let's say we have the one use case would be like video encoding. Let's say we have a function that just takes an S3 URL and then another S3 URL. The first URL has a link to a video. The function itself encodes the video to whatever that you want it to, and then it puts the newly encoded video into S3 via the other S3 URL provided as arguments to the function. Well, this can only happen if the jail itself has an IP address. So we need IP management. So I had to write an IP allocator. The pros, well, you can say you wrote one, which doesn't really carry much weight. But the cons, you have to write one. And then you have to manage a pool of IPs, which can be somewhat tedious, especially if you've got an old ornery network administrator who doesn't want to give you even the tiniest CIDR block. All right, so we're gonna we're going to skip over, we only have 15 minutes left. We're going to skip over what the IP allocator looks like. I'm sure everybody can dig deep and use their imaginations and figure out what that code looks like. That's the least interesting bit of this. If you're going to do this for real, though, use VNet. All right, so the API. First things first, we need to know our API is good, so we put a health check on it. That's not the best health check, it just returns 200. Some downstream service could be bad, and we don't know. Our service is good, so that doesn't really provide true health. Something could be sick and not necessarily dead. Either way, we throw that on there. The next is our API v1 function path. This receives a post request, and this is what's responsible for taking in the JSON payload, decoding it, and then executing our jail depending on what those parameters are. The system we have here for reference, which I'll provide links for, has operations for jails for listing out the jails, listing out all the functions that are currently running. Maybe you've got some zombie processes. Maybe you have downstream services that can be deadlocked. You can send in delete messages and actually kill the jail and reallocate the IP address back into the pool, because that's the fun part, the IP addressing. That's not overly interesting. So let's take a look at the actual, failure to be ready. GitHub.com/Brian Sky Island. So called it Sky Island for what I believe to be clever reasons, but we all know what happens when we try to be clever. So let's take a look at the HTTP service real quick. So we have, in here, we are using Gorilla Mux, nothing overly interesting. We add our handlers, we set up our services here. Health check, ever so useful. Return a 200 and do nothing. Auth wrapper, the administrative functions on the API are protected by basic auth. Basic auth works perfectly fine if you're going over TLS SSL. Anything beyond that would be over-architecting, in my opinion. OAuth is just too much. Let's take a look at the function execution. So we're going to bounce around this file a bit. Let me make this just a little bit bigger. So in here, we define our function request, and we have our URL, our call. In here, we take an IPv4 or an IP4 field, and it's a Boolean. It just says, yes, we need an IP address. If that's there, if that's present in the call, we'll get an IP address from the allocator. We can also then control caching. So let's say, for instance, we push new code up for our function into the Git repo, and we already have the Git repo cloned. We also have a binary already built. If we provide cache bus true, it will force the system to reclone that repository and rebuild the subsequent binary, and then store that until it may receive another cache bus request. Our response, as we've seen before, is our timestamp, and our data, which is just a string. Let's skip that and go down to, excuse me, function handler. So we're collecting some metrics. Don't really need to care too much about that. We read in the body, make sure the request is good. Once we get in the body of the request and we make sure it's good, we generate a UUID and we create our jail. Upon creating the jail, or which one is this? You know how like you write code and you write code from a year ago, you hate that code? I'm kind of in that boat right now. I'm trying to. What's that? This code is garbage. a lot of it is pretty bad. Thank you. All right, so we're gonna create our build jail. We're gonna build the binary. No, we're not. See, that's why that's confusing. Either way, we're gonna check to see if cache bust is true, and then we're gonna remove the repo. We're gonna go down here and we're gonna set the URL to nothing, so the binary is not saved. In terms of the binary, all we're doing is saving a path to the binary itself. We're not going to put the binary into a cache necessarily. That would be kind of big and bloated. Go binaries tend to be big and bloated only because of the packaging and the runtime, et cetera. Get past all the cache. And we come down here to the part that I do remember and understand, being the build. We have our build result, come down here to execution. We get our execution result. The execution result then is whatever that function has output. It gets then captured. The return of that gets written to standard out, and we're just doing a shell execution where we capture the result, and we take that result, and because it's in bytes, we turn it into a string here and return it. So let's take a look at the build really quick. Let's execute. So it's pretty straightforward. We come in here, we separate the URL, we generate. So the meat and potatoes of this whole entire thing is right here. Not going to go through this line by line. That's kind of boring. So the idea is to build the binary, take that binary, stick it into like a temp file system, take that binary, stick it into the execution jail, and execute. What we do, though, in the build portion, the build stage of this process, is we take this text template here, and this text template gets written out to a main.go file. That main.go file then gets compiled, and that's the binary. So in here, we have our import path, which is the path that matches up to our github.com/briandown/smile, for instance. And we take the package name that gets parsed out above, and then we do fumpt.print packagename.call. So the call, if you remember from the request, was the actual function with the left and right parens, and then any kind of parameters that the function would need would go in there. So really what we've done is just use text template to then get parsed, and this portion populated with the function call itself, and we output to standard out what's actually happening. It's really not magical at all. So this is the heart of the actual system itself. So once we have a struct here for template data, our package name, import path. The package name is necessary, so when we go to import that, it exists. It's been cloned and exists in our GOPATH, so that when the compiler runs, it knows where to get the code itself to actually compile everything. Let's take a look at the execution really quick. So we're doing a lot of OS exec, basically, to run the jail 8 command with all the necessary parameters. We've got a couple security concerns of, let's say you write a function that actually creates a jail, and then it creates a jail, and now we've got this turtles all the way down denial of service on ourself, which can affect the host system depending on what's going on. So we set children max to a configurable parameter. Generally, base configuration is 0. And we also set a timeout on our jail. So the only chance, so we provide no ability for the jail and the function itself to execute any longer than it necessarily needs to execute. The path to the jail, what the path to the jail specifies is the ZFS data set. So whenever you call jail on a process or the jail syscall, you have to provide a what's called change root command to let the operating system know that it's not just necessarily an execution, a process execution that's been imprisoned, but you want it to be imprisoned, and you want it to be imprisoned and execute within a certain place on the file system. This is what the ZFS snapshot or clone is doing. We lock it into that file system so it has what it needs. If it does any kind of like nefarious behavior in terms of file writing or anything like that, it's inside the jail. It doesn't affect the host system. Let's see. We allocate for execution, we allocate our IP address, and then we execute with all of our function arguments. This returns the byte slice that we saw down here get turned into a string. So really you can think about it from this perspective. The request comes in, we populate a template. That template, those bytes in the template then get written out to a file. The compiler runs on the file, and then that artifact, that binary that gets generated, gets put into a jail, and then that jail executes, that jail goes away. That's pretty much the basic flow of how this is going to go. Let's see how much, oh, I only got 5 minutes. Quick questions? Any questions at this point? All right, so let's. Further considerations, rate limiting, circuit breaking, additional authentication methods. We would probably want to make sure that we're not executing functions to downstream services that are reporting unhealthy. We also may want to make sure that we're not taking in a whole bunch of post requests that may be trying to perform a denial of service on us, so we rate limit inbound requests. The cache. Already really went through that. We don't have a lot of time left. The cache basically is the concept of Git cloning and reusing that Git clone, and also the binary and the path to where we're storing that binary and reusing the binary when necessary. Git Repo Cache.
But the build rebuilds that.
The build rebuilds.
Each time there's a request, the jail gets rebuilt.
Yes. So it gets built inside a build jail. However, each execution gets its own fresh jail every single time it's executed. We could potentially distribute this system around, maybe putting the binaries in Dynamo, in Redis, or anywhere else. That way we can have any number of instances being able to run any number of functions at will. So what does this do? What does this also do for DevOps? Sometimes we work in large corporations that are not very friendly to the GPL, keep it at that. And sometimes you're not allowed to use GPL licensed software. So sometimes we may have to build our own system. We may not be able to do certain things. So what this provides us is the ability to take a concept like generating our own binaries for function execution, and we can now have CI/CD pipelines fairly simple with just trivial functions being written to facilitate testing or deployments, whether it be through curl or just running make or any number of things. Monitoring systems. An event happens, well, trigger an email, okay? Call that function, maybe the argument to the function is an email address. You now have an easier means of sending this out. Is it necessarily reproducing a lot of other systems? Yes, but it's not necessarily locked to just those functions. Another nice thing is that as organizations grow, we end up getting a lot of legacy code and a lot of business logic that when the next new shiny thing comes out, we're not necessarily going to take all of that business logic and re-implement it in a new language. It doesn't make sense from a business perspective a lot of times, and we also run the risk of introducing new bugs that we necessarily didn't need to introduce. Let's say, for instance, in 10 years, Go is still around, and we've got a lot of business logic in Go. Well, maybe the next new thing is Nim or Pony or something along those lines. You can just make an HTTP call to the existing business logic and have all that same functionality, provided you're not within a very performant required situation. Examples of how you would call the system. There's client code in the repo, so you can just call a new client, call the function, and it returns. Python is even simpler. The client code for that just allows for simple execution. Any kind of code that you have in Go, you now can run it inside shell via curl or Python. Or if you're a masochist and you're stuck in a C world and all of the new kids wrote all their stuff in Go and you can't and you still have to write C, you can take advantage of it still, and there's even a C library for it if you're a masochist. Curl, we're not really going to jump into the client code at all. So I said I rewrote all of this in C as well. After writing it in Go, it was fun. It was pretty neat. It got a couple people's attention, and that was kind of neat. But I re-implemented it in C and embedded V8. I embedded the Python interpreter, embedded the Lua interpreter, and it made actually executing all of these it made executing code for those VMs just extremely simple, and to be able to control what functions were even exposed from those VMs in the actual system itself. So the conclusion really is through the use of ephemeral jails, a simple API, ZFS, and Go primitives, we can derive platforms that allow for the creation of dynamic workflows, further extending the capabilities of distributed code execution. Well, yeah, but it just allows for more dynamic code reuse and not necessarily building full-scale applications to be contextually locked to one function and then deployed. You can just really ad hoc piecemeal your code and actually have execution outside a full application. And on that, I'm 33 seconds over. That is it. Any questions? Yes?
What can you tell us about BSD Now?
BSD Now?
Yeah.
As far as I know, it's a podcast, a video podcast.
Okay.
Oh, okay, yeah. Hosted by Alan Jude. Yeah.
Is the ZFS, is that helpful because we have to create so many jails and
Yeah, so ZFS is helpful because you can create a base jail, and you can think about it as just a file system. So how it gets set up is FreeBSD operating system has just a package or a file and directory layout. So you can then take that top level directory as your root, and you can then snapshot that via ZFS and keep the snapshot as your clean base and clone from there into the execution jail. And every time you do a clone off of that base snapshot, you have a deterministic file system and execution environment. Any other questions?
Is this just like a learning exercise, or do you use this somewhere?
I use it for myself a little bit here and there. Really, the idea came from actually standing on the shoulder of a number of giants. So Liz Rice did a number of talks on building containers from scratch using Go. Then I took that with her permission, thankfully, and did a Go meetup on building containers from scratch. And we went through the exact syscalls necessary to build a container and run it, and to get a shell and all that. So then Josh Baker, local guy who goes to the meetups, kind of did a similar system using Linux and taking that same concept of the containers from scratch. Not really a Linux person, so I figured, how do I make this work on BSD? And then how do I extend it out to be a little bit more of a usable system? So I kind of use it myself here and there, but not really. That's why I prefaced in the beginning, don't let it even see production, let alone be next to production or anything like that. This is more of like, oh, this is an interesting idea. Let somebody who's extraordinarily intelligent take it and then do something maybe if they want, and that's not me. So just, any other questions? Cool. That's it then. Thank you very much.